Hello, welcome back. In this video we'll talk about matrix multiplication. Okay, and then for matrix multiplication we're going to start with two matrices, and the dimensions are important. So we're going to start with the matrix A, which is from R m by n. Okay, so this is like before, and then we're going to use another matrix B whose dimension, now B cannot be of arbitrary dimensions. For matrix multiplication to work, B has to have the same number of rows as A's columns if we want to do A times B, that multiplication AB. Okay, so we're going to consider for now this matrix. Okay, and then the elements, so we are going to say C is defined as AB. Okay, so this is matrix multiplication, and in which case the Cij, right, so which is so this is basically the matrix multiplication, right. So matrix multiplication, and in this case A goes first and B goes second, and the order matters for matrix multiplication, which we will see in a minute. Okay, so AB is not equal to BA in general for matrix multiplication. Okay, so the Cij is defined as a summation over L equal to 1 to n of A I L B L J, and then in this case the I, this I can run up to m, 1 2 up to m, and the j runs from 1 to actually this k, right, this k. Okay, now this might sound a little bit, if you have not seen this first before, might look a little bit daunting as to what this means, right. So all this means is very simple. So if you this is just math notation. Sometimes these symbolic notations very convenient to write because very convenient to program, but I have seen that they can be a little bit daunting at first to get used, and what they mean is not immediately obvious unless you are very familiar with this kind of symbolic language, right. And there is a lot of work done by many professors about whether symbolic mathematics, this kind of writing, which is correct way of mathematical writing, whether that's really helpful for intuition, because we don't think in this term, right. Now this is great for writing mathematical equation like this. This is great for doing computer programming, which we will see later. But let's see what this actually means. This means we are taking from matrix A, we are fixing the row. If you see, I is fixed in this equation and j is also fixed. I is the row, right. So in the C matrix, which is the resultant matrix of this matrix multiplication, the ith row, jth column element is formed by taking this ith row of A matrix, matrix A, and then we are iterating over all possible values in the ith row, and then multiplying that with the jth. If you see here L is varying but j is fixed, so the jth column of B, right. So when we work an example, actually this will become very clear. So I'm not going to go more into theory because already maybe this is confusing. Let's take an example, right. So this is example 2.3 in the book. So if we take A equal to this matrix 1 2 3 3 2 1, okay, so that's this matrix, and this is an element, as you can see, 2 rows and 3 columns, 2 by 3, and then we are going to take B to be equal to 0 2 1 minus 1 0 1, okay, and this is, as you can see, how many rows, there are 3 rows and 2 columns. So this is 3 by 2 or 3 by 2, right? Now in this case, let's look at AB, right? Now to get AB, so we have to get the first element, that's going to be, this is C, right? So this is C, which is the C equal to AB equals, so how do we know, let's see the dimension of this. We know that this C, from here you can see that it has I rows, M rows and K columns, right? It's going to be M by K, which means in this case, if you can see here, this A, this 2 corresponds to this M, this 3 is N, and that 3 has to be the rows. So that works. Now this can be anything. It just so happens that this K is 2 in this case and M also is 2, right? So let's first do C equal to AB, right? So to do that, I'm going to take the first row of A, which is this one, the top left item here in this matrix C is going to be this multiplied by this, right? Which means we take this row and then take 1 times 0. So I'm going to write this as 1 times 0, right? This dot is, okay, let me write multiplication, 1 times 0 plus 2 times 1 plus 3 times 0. That's the top left element. So this, the first row here and the first column here are multiplied, right? 1 2 3 times 0 1 0. And then for the next this element, right? So this is the first one. Then the only next thing we do is take this row, multiply by this column, right? So that's going to be 1 times 2 and then plus 2 times negative 1 plus 3 times 1, okay? And as usual, the precedence is for, you know, if you remember from school days, it's PEMDAS or GEMDAS, so multiplication precedes addition, right? So we'll first multiply these terms out, all these terms out, and then add them up, okay? So same way, let's fill this up. Now this is going to be 3 times 0, right? So now we have moved on to the next row. This 3 2 1 multiplied by 0 1 0, 3 times 0 plus 2 times 1 plus 1 times 0, and then same thing we do here, 3 2 1 and 2 minus 1 1. So that's 3 times 2 plus 2 times minus 1 plus 1 times 1, right? And that's about it, right? And this matrix, as you can see, this dimension is now gone, right? This if you want to think of it as the inner dimension, right? The outer dimensions remain, the 2 by 2 remain, right? And then this we can simplify now, this to be equal to, so this is 1 times 0, this is 0 plus 2 plus 0, so this is 2, and then this is 2 minus 2, so that's 0 plus, so this is 3, and then here we have 3 times 0, and then this is, so again 2, and this one is 3 times 2, which is 6, minus 2, that's 4, 4 plus 1 is 5, right? So that's 5, right? And this, as you can see, is an element of R2 by 2, okay? So that's this matrix C, right? And surprisingly, in this case, we have the same number of columns in B as there are rows in A. So in this case, we can also do B times A if we want, right? In which case we put B first. So let's do that. Actually, I'm going to write it 0 2 1 minus 1 0 1. That's B times A. So that's 1 3 2 2 and 3 1, right? Now why is this going to work? This works in this case because this is a 3 by 2 matrix and this is a 2 by 3 matrix. So fine, these dimensions match. This 2 is same as the columns here, the 2 is same as this rows here 2, right? So this works, and then the resultant matrix, obviously this inner dimension will be gone, it will be 3 by 3. So let's see how to do that. In this case, it's going to be, let's see, so 0 times 1. So I'm going to just go through this without writing it laboriously like this. So 0 times 1 is 0, 2 times 3 is 6. So 6 goes here, okay, and then the 0 2 2 2, right? So we take for the next one the same row and then the column moves, right? So 0 2 0 times 2, this first one is 0 times 2, that's 0, plus 2 times 2, that's 4, so 4 goes here, and then 0 times 3 is 0, again 2 times 1 is 2, so the 2 goes here. Okay, and then 1 minus 1 1 3, we take this 1 multiply by 1 and then minus 3, so that's negative 2, and then 1 times 2 and then minus 2, that becomes 0, 1 times 3 and then minus 1, that becomes 2, then this 0, so this just basically 0 times 1 is 0, 1 times 3 is 3, and then 0 times 2 is 0, and then 1 times 2 is 2, and then this 0 times 3 plus 1, that's going to be 1, right? So this is now an element of R3 by 3. Okay, so from this example, obviously we know that for matrix multiplication, AB is not equal to BA in general. Okay, even the dimensions don't match. Okay, another thing to note is it just so happens that the answer is actually all these matrices are what are known as square matrices because of these dimensions we have chosen. These need not be, the results need not be always square matrices. In this case it was a 2 by 2, in this case it was a 3 by 3, but that's not always the case. For example, if you take a 2 by 3 matrix multiply by 3 by 4, your answer is going to be a 2 by 4 matrix. Okay, so that's about matrix multiplication. Now let's go back and read a little bit from the book about what they are talking about, right? Anything that is relevant that we might have missed, right? So this whole thing is called what is known as a dot product, right? So dot product. So what we do to compute each one of these elements, if you remember, this thing, this one, this one, this one, all these, in fact when we write, you take this vector and then this vector, this is nothing but a, if you want to call this row as A1, right? So you take this A1 and then you basically multiply this by, actually that may not work, A1 is, it's a little confusing. Okay, so let's forget about that. The dot product, the best way to think about it is actually with this, right? So there are n columns in A and then n rows in B, right? So that's basically n columns in A and n rows in B, and then we just write it, we just take this and then multiply with this, because this becomes a 1 by 3 matrix, this becomes a 3 by 1, the result is a scalar. So dot product is always going to be a scalar. So this is definition of dot product, so they're talking about that. And then they talk these as neighboring dimensions, right? So the neighboring dimensions of the matrices should match, which means when you put them together like this or you put them together like this, whichever dimensions, the neighboring dimensions, in this case it's 2, right? In this case it's 3 will be the neighboring dimension when you put A and B together. So those should match and only then it is defined. And then they are talking about this BA will not be defined, is not defined if m, actually if m is not equal to k. I think they have a typo in the book, because this one BA, so here we have B is 3 by 2, right? So this is K, right? So when is AB defined? AB is defined only if, so if you take any two general matrices, then AB is defined only when this column is equal to this, right? And BA is defined only when this is equal to that. I think they have a typo in the book where they said m not equal to n, right? It's m not equal to k. So the product, so they are writing the product BA is not defined if M is not equal to N, since the neighboring dimensions do not match. I think this, so if you look at BA, is going to be B is N by K and A is M by N, right? So this is not defined when K is, M is not equal to K. So this should have been K in the book. At least in my copy they have written M not equal to N, right? So maybe that's a feedback we can give it to them, so they correct it. And then matrix multiplication, so they have a remark. So let's see, matrix multiplication is not defined as an element wise operation on matrix elements, right? So don't get confused by this, right? So Cij is not equal to Aij times Bij, right? For addition, this is what we used before, right? If you remember, for addition, if you see here, we have used indeed this, right? So Cij is Aij plus Bij, right? But that's not true for multiplication, right? For matrix multiplication is defined this way. Cij is, you take this whole row, do the dot product with the column, right? The kind of element wise multiplication often appears in programming languages when we multiply multidimensional arrays with each other, and this is called this kind of thing where you this is not true for matrix multiplication, right? But there is something called a Hadamard product. Right there, it is in fact defined this way, right? Cij is actually equal to Aij Bij, right? Where you just take the elements. In that case, obviously you need to have same dimension for both matrices. That is another thing, right? So if they are not same dimension, then even that is not defined. So Hadamard product is not, so this is different, right? So this, okay, so let me maybe explain with an example what this means, right? So where we have Hadamard product, right? They are not talking about this in book here. Hadamard product, right? Element wise multiplications, right? Where you say Cij equal to Aij times Bij, right? Then I equal to 1 2 to M, j equal to 1 2 to N, but these matrices are same size, then only this whole thing is defined, right? So that's the Hadamard product, which is not equal to matrix multiplication. Okay, so that covers that part, so there should be no confusion there. Okay, and then couple more things. So there is this definition of what is known as an identity matrix. What is an identity matrix? If you remember from school days, hopefully you've studied identity matrices before. So identity matrix, right? So in general, if you take for example 2 by 2, then this is the identity matrix, which means only in the leading diagonal you have ones and then everything else is 0, right? So leading diagonal is ones, everything else is 0. Okay, so that's the identity matrix. Now why is this called the identity matrix? It's called the identity matrix, and it's generally denoted by this this notation I subscript n, right? So this belongs to R n by n, right? What does this mean? If you have n, so you'll have n diagonal entries all 1, everything else 0, right? And you take any matrix A, right, whose dimension matches this, right? In this case A also has to be a the dimensions has to match, right? So for example, let's take this identity matrix, and if I take A to be equal to some matrix, right, 4 5 minus 1 minus 6, right? So if I take this is I2, right? So this is how I2 is defined, right? I2 is just in the 2 dimensions. Okay, now if I take I2 and multiply times A, this is nothing but 1 0 0 1 and then 4 5 minus 1 minus 6. This can be any numbers, I'm just giving you an example. If you see, automatically when we do 1 0 and multiply this guy, these 4 5 are going to come out, right? Because it's 1 times 4 and then this is 0, and then 1 times 5 and then this is 0, and then 0 times 4 and then 1 times negative 1, so that becomes negative 1, and 0 times 5 and 1 times negative 6 becomes negative 6. So we get this back, right, equal to A, right? So we got the A back. And then same thing, A times I2, right? It doesn't matter, because if A times I2 is going to be 4 5 negative 1 negative 6, then we have 1 0 0 1. You can see the same thing going on, right? 4 times 0, in this case when I multiply, it's 4 times 1 plus 5 times 0, so that becomes 4. Then 4 times 0 plus 5 times 1 becomes 5. Negative 1 times 1, and then this is 0, so this is negative 1. And again negative 1 times 0 is 0, and then minus 6 times 1 is minus 6, so this is also equal to A, right? So this is why it's called identity matrix, because when you it's like, it acts like 1 does in multiplication, right? In regular number scalar multiplication, 1 is known as the identity for multiplication. So same thing, this IN is known as the identity matrix, right? This is with respect to multiplication. Okay, so we'll look at some properties and then we'll close this lecture. So now some properties of matrices. So we'll go to some properties. This you might have done in school days with just simply numbers, right? And then with some regular multiplication and so on, right? But now we'll do with matrices. Okay, so associativity. What does this mean? So for now, you remember this from the symbols. For every A belonging to R m by n, B belonging to R n by p, C belonging to R p by q. Okay, this is associativity of matrix multiplication. Okay, so then they are saying AB, you do AB first, multiply them, and then multiply by C, and it all works because AB will work because you see the inner dimensions match, and then the resulting matrix, this AB itself will be m by p, right? And then the p matches with the C, so this is defined, and this is equal to A times you do BC first and then you do this, right? So BC, again this is going to match because this is going to be n by q, and then you take that n by q and this is m by n, so that will be m by q also, right? So both the dimensions match. So this is associativity, right? So that's the first one. Second one is distributivity. Right? And in this case, for every AB in R m by n, and then CD in R n by p. Okay, so these are the given conditions, right? And then this means for every AB in R m by n, and then for every CD in R n by p, we can have, we basically have this true: A plus B times C is equal to AC plus BC, right? So this is distributivity from the right hand side, and then from the left hand side it's A times C plus D equal to AC plus AD. Okay, this is another property. We don't need to prove these proofs, little bit more math, we should be okay without. I think these are intuitively clear. These are clear in terms of scalars, but then if you look at it, what this element is going to be, the way that these can be proved is, let's take this statement, right? The left hand side, the resulting matrix, what will be the ijth element of that resulting matrix, right? So you know that when you add these two, you will get aij plus bij as the element here for this one, and then you take that and you basically have the C matrix which is n by p, right? So that's how you will look at the ijth element here, right? And then you will prove that when you take A alone and multiply times C, that will become that dot product that we talked about in the previous lecture. It will be like that, like this. So let me go back to that. Like this, right? So in this case we have A and C, so it will be this dot product like that, right? So basically you just take the row and column and you multiply the two, and then you will get that element, and then when you add that element, then algebraically you can show those two to be the same, right? I don't know if we need to actually work through the proof, but if you are interested, you can try it, right? And then the third one is what we discussed before, which is the multiplication with identity matrix, okay? M for multiplication here, right? And this is like this for every A in R m by n. Now you can see that this is m by n, which means matrix has to multiply from the left, im times A, right? If I want to multiply from the left, this is m by m, right? And this is m by n, right? So that's A, right? A is an m by n matrix, right? So this is this obviously is going to be equal to A, right? And so is, and if I want to multiply with the identity matrix in the right hand side, I can do A again, but this is m by n, which means I have to use I subscript n here, right? So n by n. This is also equal to A. Now this maybe so if m and n are not equal, it looks a little bit weird, but let's take an example, right? So let's take in the previous page, we saw one example where we took a 2 by 2, right? In this case, A is 2 by 2, right? Now let's take a slightly more complex A equal to 2 by 3 matrix, okay? So what we are going to do is, because I'm going to take m equal to 2, n equal to 3. So let's take A equal to 1, 5, 6, negative 2, minus 1, 0, okay? Some random numbers here. Now if I multiply this matrix by on the left hand side with an identity matrix, the identity matrix has to be 2 by 2, right? So this is basically an element in R 2 by 3. So for left multiplication, I need to do I2 times A, right? Which is nothing but 1, 0, 0, 1 times 1, 6, minus 1, 5, minus 2, 0, right? And then this, as you can see, is going to 1 times 1, and then this is 0, so it's just going to get this first row back here. So 1 times 1 plus 0 times 5 is 1, 1 times 6 plus this is 0, so this is 6, 1 times negative 1, so that's, and then the 0 times 0 goes away, right? So you are getting the first row of A. Same way you can do the math and see that this is going to give you 5 minus 2, 0, which is again equal to A, right? But what about from the, if I want to multiply this from the right hand side, right? So I'm going to, unfortunately I ran out of space, so I'm going to, bear with me here when I write it here, okay? So I'm going to take the same example and then write A times I3, right? Because on the right hand side, if I multiply, this is 2 by 3, which means this has to be 3 by 3, right? And identity matrices are always same dimension for both rows and columns. They are square matrices, right? And this one, A times I3 equals, okay, so let me just draw that, 1, 6, negative 1, 5, negative 2, 0, and then we just take this and put this into 1, 0, 0, 0, 1, 0, 0, 0, 1, right? This is the identity matrix in 3 dimensions, right? And again you can see this all this is going to do is it's going to take this, and then these two are 0, so only the 1 is going to come back, right? Because it's 1 times 1 plus 6 times 0 minus 1 times 0, you add them up, you get 1. The same thing here, only the second element exists, right? Because 1 times 0, 6 times 1 plus then minus 1 times 0 all cancel, and then here only the last element exists, and then same thing here, right? So 5 minus 2 0, right? So this is again equal to a. So that is this multiplication with identity made this property, right? Im times a equals a, and a times in is also equal to a, and in the book they have written this whole thing combined as im times a equal to a times in equal to a, right, which is the same thing. Okay, all right, so with that we'll close and we'll see you in the next video.